Welcome to homework.
In this problem, we're going to be looking at the effect of reduced mass on the energies of transition changes. So specifically, if we go from principal quantum number n equals 2 down to the ground state n equals 1, we want to know two things. We want to know what is the coefficient associated with the energy of that state. So typically, if you're talking about a hydrogen atom, you're going to get 13.6 up here, but let's just call this C for some constant. What is this number going to be? And I'll show you what I mean in a second. And secondly, what we want to figure out, which is very much related, is what is the energy associated with the transition. So what is basically the energy of the photon that's going to be emitted during that transition. So to start, let's just say that our reduced mass is equal to the typical reduced mass of a hydrogen atom, in which case we're going to get our familiar value or expression. We're going to say that E sub n is going to be 13.6 divided by n squared. And so if we have n equals 2 going down to n equals 1, what we're going to have is negative 13.6 from the final state down to the initial state. So we're going to have essentially 1 over 1 squared minus 1 over 2 squared, which is going to give us 1 minus 1/4, which is 3/4. So the energy delta E, which is going to go into the photon, is going to be 3/4 of this 13.6, which is going to be 10.19. It's going to be electron volts. So that's the energy of a photon emitted during hydrogen atoms transition from n equals 2 to n equals 1. So that's our first result, and that's for the reduced mass being equal to the typical reduced mass of a hydrogen atom. So let's record this over here, shrink it down. Okay, so the next scenario we're going to talk about is what if we had a reduced mass that was equal to 1/2 of the typical reduced mass, which could correspond to a situation where you have positronium. So in this scenario, if we're looking at the energy, we want to know what this coefficient is here. We can actually just look at the expression for E sub n when it's expanded out. You can look in the book for the derivation here, but it's going to be negative the electric constant squared times the reduced mass times e to the 4th over 2 h bar squared. But what's important here is to realize that the reduced mass is in the numerator. So if we take 1/2 of the reduced mass, I'm just going to stick this down here for reference, 1/2 of the reduced mass is going to give us 1/2 of this coefficient, right? Because the energy is directly proportional to the reduced mass. If we cut this in half, this has to go down by half. So what we're actually going to get for this expression this time is going to be exactly half of what we got before. So this is going to be negative 6.78 divided by n squared. If we go ahead, again, we're going from 2 to 1, so we're going to get 3/4 of this value as the energy that is attributed to the photon. So for that value, it is 5.10 electron volts. Okay, so that's our second result for the positronium. The third result, you are told that the reduced mass is equal to 185.8 times the typical reduced mass of a hydrogen atom. So this could correspond to a situation where you have some muonium, which is an atom composed of a muon and a proton, which you could look up if you'd like. But what's important is that, again, we know that E sub n is directly proportional to the reduced mass. So if we take 185.8 times the typical reduced mass, our expression for energy is going to jump up by that same factor. So we're going to take that 13.6 that we know and multiply it by 185.8, which is going to give us as a value 2,525 electron volts, and this is going to be negative again over n squared. If we go ahead, apply the same process to get the energy of the photon, we'll get 75% of this. which is going to be a value of 1,894 electron volts. So that's the energy of the photon. And so this is our last result. And so this has been sort of an exploration on the effect of the energy of a transition as a result of changing the reduced mass.